Hey everybody! Alright, so what are we going to do today? We're going to learn about the life cycle of a star. So what is the life cycle of a star? Well, first, it's important to know that there are many different types of stars at all different sizes and colors and temperatures, but we are going to focus on the main sequence stars because that is what type of star our sun is. It is a main sequence star. Okay, well, first let me show you real quick the different types of stars. Okay, so we've got all the different types of stars, and it shows time and it shows mass. And those are really the big factors that divide the different types of stars. So what we've got here are protostars, and they're protostars of different sizes. So where's our main sequence star? Can't see very well. So down here probably, yeah, because I see a red giant right here, planetary nebula, red giant here. I would say any of these could be main sequence stars, probably these three right here. It's very gradual. We start out as a fairly small protostar, probably one of these two. And then we stay at about the same temperature and the same size and the same pressure for billions of years as we have so far. And then, towards the end of its life, it becomes a red giant. But up here we can see that as the mass gets bigger, it starts out as a protostar. They all start as a protostar, but they change a lot throughout their life. They start out as pretty big supergiants, blue supergiants, and then they cool off pretty quickly. They start out huge, they cool off faster, and then they do these huge explosions. They're so big, they have such a large amount of mass that some of them become black holes at the very end of their lives. But ours is very, very calm compared to the rest of them, very, non-changing. And then at the very end, our sun swells up, and then we kind of just lose our temperature slowly and gradually. Okay, so now let us look at the main sequence stars. And to do that, we will look at what astronomers look at, which is called an HR diagram. HR actually stands for guy's name, so we don't really need to know what that stands for. So what we've got here is a comparison between temperature, luminosity. Sometimes there's a comparison between like a brightness. So as you can see, we've got our main sequence stars in the middle, and they follow along a very linear curve. And then we've got our white dwarfs, which are really small but really hot. So we've got our hot temperatures up here and our low temperatures down here. And then we've got our supergiants and our giants, which are fairly cool but huge and very explosive, as we talked about before, at the end of their lives. So main sequence stars actually fall on this curve as they're aging. So they can start out up here pretty hot, pretty warm as protostars, and then they just burn and burn and burn and gradually cool off. And sometimes they kind of swoop over here into the white dwarfs. Actually, often they do. And the brown dwarfs over here, a little bit cooler. Okay, so that's our HR diagram. So let's look at our sun and what is going on within our sun. So we've got different layers, just like in the Earth. We've got our core, we've got our inner core, which is known as the radiative zone. Then we've got the outer part, just before the shell, which is called the convection zone. Then we've got our we've got our chromosphere, our photosphere, which is not shown. Then we've got our corona, where the glow, this is basically what we see during the middle of the day. And then we've got our streamers. Okay, so there's actually two processes that we need to focus most on. There is nuclear, let's look at this real quick again. There's nuclear radiation, or basically nuclear fusion, and that's going on in the radiative zone. And then there's convection. Convection's pretty simple, and I'll touch on that in just a second. So let's look at nuclear fusion first. Sounds pretty intense, I know. But in reality, it's pretty simple when you think of it on its most basic terms. Nuclear fusion involves, within our sun, we have hydrogen, which is the most abundant element in the universe. And we've got tons of it in space. And tons of it in our sun. And they are moving around at huge speeds, huge temperatures, huge pressure, and they have to, just be colliding nonstop. Well, because they're at such huge temperatures, and because they're such small elements and particles, they do something what's called quantum tunneling, and I won't get into that, but basically what happens is they collide, and they give off tons and tons and tons of energy. And in the process, a new element is formed, and that is helium. And that's really what nuclear fusion is. It's fusing two smaller elements, two smaller atoms together to form a new element. Okay, so the next process we need to look at is convection. Convection is very, very basic. It is simply hot warming up cold. So we've got a hot source, we've got a cold reservoir, and it's just warming up that reservoir. Heat in physics basically always moves from hot to cold. So, and that movement causes an actual fluid flow, and that is what we call convection. It's hot air moving to cold air warming up, moving over to the hot area, and then cooling down, moving up again, and it's just this constant flow, and that's basically convection. So now that we understand the processes involved, we can understand the life cycle of our star. So our star actually starts out as a bunch of particles in a nebula, and a nebula is really just that. It's just a bunch of particles close together. Gravity has pulled on them so much so that, they've stayed together. They continue to be pulled together by gravity and condense, continue still into a globule until we're at the point where we have a protostar. And actually, billions of protostars can be built from the particles that are within a nebula. So our protostar is actually very unstable. Why is it unstable? Because the radiative zone is going crazy. This guy is just creating so much energy that, it's just swelling, condensing, swelling, condensing. It's just a very, very unstable element. But as it burns off all of its hydrogen, or starts to burn off some of its hydrogen. The hydrogen lasts for billions of years. But as it starts to burn stuff off, more energy is released, and then things start to balance out to the point where gravity and that pressure of the radiative zone can balance out. And that is when we come to the point where we are now in our own star, which is just staying at the same temperature for billions of years. And then once it gets to the point where it wants to, retire, it becomes unstable again, and it is basically those forces that have unbalanced. The star becomes lighter because it has burned most of its hydrogen, and then the radiative zone actually becomes much stronger than gravity, and it starts to swell. And it just keeps swelling. It keeps getting bigger and bigger and bigger. Our sun will actually go beyond the Earth's path that it goes around the sun. It's going to actually swallow us up in about 3 billion years or so, 4 billion years. So we won't be around, so we won't have to feel it. So we'll be alright. So it starts to swell, and it gets bigger and bigger and bigger, to the point where gravity takes over with one final burst. Energy is just exploded everywhere, and it's not a supernova. It's really just like getting rid of like its dead skin, kind of. And then it just chills out. As a white dwarf for the bigger ones, black dwarf for the smaller ones. And they're still really hot. I mean, we couldn't stand on them even at the temperatures that they are as old grannies. But that is our life cycle of a star, of our main sync star.